Well, hello everyone, and a good Wednesday night to you all. Thank you so much for being here today to hear our NSF NCAR Explorer Series talk titled "What Can Clear Skies Teach Us?" An urban air. Oh my goodness, I already forgot the title. A history of urban air quality. My name is Evan Portier, and I'm an educator here at NSF NCAR, which stands for the U.S. National Science Foundation, National Center for Atmospheric Research. Don't worry, there'll be a quiz at the end of the lecture for that. Otherwise known as NSF NCAR. NSF NCAR is a world-leading organization dedicated to understanding Earth system science, including the atmosphere, the weather, and even the sun, and how all of these sciences are important to building national resilience. Now, folks, after the lecture, you'll have an opportunity to ask questions. If you are in person, all you have to do is raise your hand. We'll give you a mic, and that way our online audience can hear your question. If you're online, you're going to be using the Slido platform. Go ahead, scroll down. You'll see a Q&A tab, and you can input your questions on there. Kelley also has a few questions for us. So my folks that are in person, I'm going to ask that you use either a laptop or a mobile device to go ahead and navigate to slido.com. There's also going to be a QR code popping up right here. Once you get there, you can search for hashtag Explorer Series, and that will get you to the questions that Kelley has asked us. And there is that QR code right there. Most importantly, there's going to be a question about, let's see if I have this. You might have heard about nitrogen oxides, ozone, and particulate matter being measured in our air. What other substances do you think have been measured in urban air? And I will give you a little hint. Think outside the box there. Just for you all to know, this event is being recorded and will be available on the NSF NCAR Explorer Series website. And with that, I'm going to do a short introduction to Dr. Kelley Barsanti, and then we'll get the lecture started. So with us today, we have Dr. Kelley Barsanti, who is a scientist at NSF NCAR in the Atmospheric Chemistry Observation and Modeling Laboratory, also known as ACOM. Prior to joining ACOM, she was an associate professor at the University of California, Riverside in the Department of Chemical and Environmental Engineering and the Center for Environmental Research and Technology. She has developed an independent and successful research program contributing to the comprehensive measurements of gaseous organic compounds and building mechanistic models to explain laboratory and field observations of atmospherically relevant organic gases and particles. Such advancements are critical for improving the model representation of emerging pollutant sources under changing atmospheric conditions and mitigating the adverse impacts of air pollution. Much of her recent work has focused on emissions and chemistry of wildfires. So, with that, let's give a warm round of applause for Dr. Kelley Barsanti.
Great. Thanks so much for the introduction, and thank you for to everyone for being here tonight, those of you in person as well as those of you online. I appreciate it on this rainy Wednesday night. So here's my title. I won't be talking about wildfires today. We ended the bio, but a lot of people have come here and in this Explorer series talked about wildfires. So I wanted to talk about some other work that I've been involved in related to urban air quality. So just to give you a quick overview of what I'll be talking about tonight, I'm going to give a historical perspective on air pollution in Los Angeles. I'm going to get a little technical, talking about some pollutants specifically and what their sources are and their health impacts. I'm going to talk about what we learned from a study we did in the LA Basin during the COVID-19 pandemic, and just a little bit about where we are now. I want to say up front that none of the work that I'll be presenting, my own work, as well as a lot of the work that I'm presenting of others, would not have been possible without federal funding support from NSF, who you've heard, NOAA, the National Oceanic and Atmospheric Administration, as well as the United States Environmental Protection Agency, or EPA. Okay, so here we are, Los Angeles in the 1940s. And one of the things that was pretty common back then was this brownish smog, which limited visibility to blocks. And the smog was actually really different from other pollution episodes at that time. So for example, in Donora, Pennsylvania, and you might have heard of the London fog, these pollution events were largely associated with burning dirty coal, so lots of sulfur being produced, and these events were distinctly different. It was thought at the time that this pollution was probably from a local rubber plant, a wartime rubber plant, but that rubber plant was closed and the pollution didn't go away. So in 1947, actually the very first air pollution control district in the US was formed to study this problem. So then along came Ari Hagenschmidt and Fritz Wendt, and they set about studying, where is this pollution coming from? What is happening here? And so some of the symptoms of the people in this environment were that their eyes and lungs were burning. Rubber tires in the car, on your bikes, were just degrading very rapidly. My PhD advisor actually lived here in the 70s and said, your plastic lawn furniture would just degrade outside on your porch. So, these were some clues what was happening. And Hagenschmidt, who's shown in both of these photos, actually suspected that what was causing these effects was ozone. And super interestingly, he thought about what possible sources there were of ozone and figured that this ozone couldn't be being emitted. It actually had to be being formed in the atmosphere. So that was really interesting. Wendt, who's not shown in either of these photos, but he was studying plants at the time, and he demonstrated that this ozone could actually cause damage to crops as well. Okay, so Hagenschmidt actually took a 1-year leave of absence from Caltech at the time to investigate this hypothesis. And in fact, he did discover that byproducts of gasoline combustion, we call them hydrocarbons or volatile organic compounds, combined with nitrogen oxides in the atmosphere, were actually forming ozone. These combinations also can form particulate matter, or PM 2.5, which we'll talk about throughout this presentation. So at that time, the Motor Vehicle Control Board was established, which eventually became the California Air Resources Board as we know it. It was chaired in '68 by Hagenschmidt, and they developed the regulations that were eventually adopted by the US EPA. And one of the things that I love about this pollution story in LA is that it's just a really good example of how science helps us investigate a problem. Engineers helped us develop the tools to mitigate that problem, and then policy and regulations came into play. And the question is, did it work? So the short answer is yes, it did. What I'm showing in this figure, this is just a timeline from 1960 through 2010. Both the red and the blue trace are ozone. I'll note that this blue dashed line is the current ozone standard. So you can see that ozone has indeed come way down since the 60s, right? So this was effective science, engineering, and policy. Over here, we have PM 2.5, which has also dropped. And so, when you think about that the standard is here, right, these were astronomically high levels of ozone. And I will just say, for any of you that have been in LA or in that area recently, even about 60 ppb of ozone, you can actually start to feel in your lungs. So it's hard to even imagine what's 400, right, these 600, 400 ppb. Okay, quickly, because I'm going to come back to this, I won't come back to this figure, but I do want to just point out here that towards the end, you see we have these very rapid declines until about the 2000, and then things do start to level off a little bit, which I'll come back to later in the talk. Okay, so I mentioned that Hagenschmidt actually found that it was hydrocarbons, so partially unburned gasoline, that was leading to ozone and PM2.5. So I want to take a look at these, what we call precursors. They're the precursors to the ozone and the PM2.5. So again, we look at a timeline here. Oops, nope, we don't do that. Let's see, there we go. Okay, so if we look at this timeline from the 60s again to 2010, basically this CO, so carbon monoxide, is a marker of combustion. And often when you measure in a place like LA, it's often a measure of gasoline combustion specifically. A lot of these other compounds that are shown here, again, are those hydrocarbons that come from gasoline combustion. They come from other sources as well. But basically in this paper, what they were saying is that for decades, we basically got this consistent reduction, and this was telling us that this was a common source, and that source was gasoline combustion. You do, again, I want to point out, you do see some bumps here and some different behavior. These are not gasoline combustion markers, but natural gas markers. So we can study these trends and these behaviors to understand sources. Okay, so this is moving us in. I've mentioned a couple times PM2.5, I've mentioned ozone, I've mentioned the California regulations, and this is getting into that technical part. I just want to take a broader look at the US, not just to California, and talk a little bit more about PM2.5 and ozone. So the Clean Air Act was signed in 1970, and it really had three functions. One was to reduce these ambient concentrations. So when I say ambient concentrations, you can just think of this as like in the airshed, right? So like it's a regional concentration of these pollutants. And we have 6 criteria pollutants that are regulated by the EPA. They also intended to reduce emissions of toxic air pollutants. So those are reduced at the source. And then the other intent was to phase out the production and use of chemicals that destroyed stratospheric ozone. So one of the things about ozone that can be a little bit confusing is that stratospheric ozone, so ozone way up in the stratosphere, is actually protective of human health. It helps mitigate or eliminate some of the UV that's coming from the sun, so it protects our health. Tropospheric ozone, so ozone formed down low, is actually dangerous for human health, and that's what we're going to be talking about most of the time. Okay, so in 1990, amendments were signed to the Clean Air Act. They were signed by George H.W. Bush. Mary Nichols, who was a former CARB chair, she's been a CARB chair appointed twice. She oversaw the drafting of the 1990 amendments. And I just have to say she's a true hero, and if you want to look her up, I encourage you to do so. I do sometimes think to myself, like, what would Mary Nichols do? And so she's just an amazing and inspiring figure. She was an environmental lawyer. So the 1990 amendments to the Clean Air Act, those are really considered the teeth, right? So they are the transportation policies, the inspection and maintenance programs, the market approaches, incentives, permitting, et cetera. And one thing I just want to point out, you've probably noticed I have some little, random bullets on the bottom. But the list of there were 189 toxics on the list. One came off. This list of 188 toxics really actually hasn't changed since 1970 or the 1990 amendments. Okay, so there is too much on this slide to read, but again, I just want to walk you through it. You're welcome at any time, to go and take a look. This is on the EPA website. These are the National Ambient Air Quality Standards. These are for those 6 criteria pollutants that I mentioned. So things like carbon monoxide, lead, nitrogen dioxide, ozone, particulate matter, and sulfur dioxide. And again, we largely focus here on ozone and PM. And part of the reason for that is because PM and ozone are the 2 criteria pollutants that we still have the most problem with here in the US and globally. So a lot of places are still in violation of these standards. The other thing I want to just point out here is that we have primary and secondary standards. The primary standards are designed to be protective of human health and specifically our most vulnerable populations. And then you'll see these concentration limits. And then there's some notes about averaging. While the list of pollutants has not changed over time, these limits have changed over time, and it's often this really complicated negotiation about what the epidemiology tells us, like what health studies tell us is safe, what is technically feasible, right? Because it could be that we want zero pollution, that's not technically feasible, and what's economically feasible as well. So it really is a negotiation, and I think that that's an important point. Okay, so some of you may have heard or at least seen this color scale for air quality. You may not really have known what it's about, but this is called the Air Quality Index. And what the Air Quality Index does is it tells you something about your air relative to the standard. Okay, and specifically, AQI is almost always calculated with respect to either PM2.5 or ozone or some combination. Sometimes it's just whatever is the highest of the two. And so again, this is a bit hard to read, but I just want to point out that if you look at the ozone, the PM2.5 standard, the 1-year standard is 9 micrograms, and the 24-hour standard is 35 micrograms per cubic meter. And those set the set points for the color scale. So when the mass loading of PM around you is below that 9 cubic meters, you get green. When it's below 35, you get yellow. And then there's other gradations here when we are above the standard. Okay. There's a global standard. This metric is also used globally. So you will see AQI index for other places in the world. And just the difference often is that the standard is usually set by that country, or if the country doesn't have its own standard, they can use the World Health Organization standards, but it is a global metric. Okay, so speaking of global metrics and health, this puts us at one of our first Slido questions, which you were asked to rank the risk factors. And we're curious, there they are. Okay, there it is. Okay, so air pollution, high blood pressure, tobacco use, child and maternal malnutrition, and high or low blood pressures. And I actually think you almost got it just right. So this is a study. It's linked, by the way, in the Slido. There is the Health Effects Institute puts out a state of the global air. This is part of their results. And they look at a bunch of health impacts and what causes those. And high blood pressure is actually first and air pollution is second. But, it's almost, I think, sometimes surprising. We think, air pollution. But globally, a lot of deaths are attributed to air pollution. I want to show that here. So again, this is another statistic from this global air. And basically the way this map is showing you the number of deaths, and they get hotter colors or higher number of deaths. And basically this is telling us that these are deaths that would occur earlier. They occurred earlier than would have occurred in the absence of air pollution. So that's just one statistics. So you might not be surprised that these highest values are in China and India, where again, the air pollution levels, particularly these are associated with PM2.5, are very high. I will say one of the things, if you look in the state of the air, they show in which countries these numbers are going up and which they're going down. And the number of deaths associated with PM2.5 has been going down in most countries over time. So this is a positive thing, again, reflecting the efficacy of science, engineering, and policy. So I always like to say, things are much better. But another statistic I think that's important to sort of recognize is that about 40% of the US population lives in an area that's in non-attainment, right? So that is, lives in an area that's in violation of those air quality standards. And again, this is most often ozone and PM2.5. Okay, so I've said PM2.5 a bunch of times. What does that mean? Let's put it in perspective. So 2.5 refers to the size of these particles. So these are particles in the atmosphere. They are both emitted directly into the atmosphere, or they can be formed in the atmosphere. And to put that size in perspective, a fine beach sand is about 90 microns. A human hair can be like 50 to 70 microns. So PM10 is 10 microns, and those are things like dust, mold, pollen. When we're talking about the PM 2.5 that's actually formed in the atmosphere, it's very small. It's 2.5 microns and less, right? So this gives you an idea of the size. And one of the things that I find fascinating about PM 2.5 is, okay, right, so it's this chemical process, these particles form in the atmosphere, and it just so happens that these particles are of a size that they interact really effectively with incoming solar radiation. So they can absorb solar radiation, they can reflect solar radiation, and this is one of the reasons that you could see smog, right? So it's one of the reasons you can see smoke from a wildfire. It's because these particles are actually interacting with light. The other thing, which is not so great, is that these very small particles also can travel very deeply into the lungs. So what this figure is showing is this is giving you the particle sizes. So we say that like less than 4.75 microns are inhalable. So I like to say our nose hairs are useful. So like our nose hairs filter out like particles that are 10 microns. And so we get those kind of trapped in our mouth. But when we get about 5 microns, they start to enter our airways. But it's only these very small particles that can get all the way down and deep into our alveoli. Also, I won't be talking about this today, but the very smallest particles that often come from like diesel soot combustion, those can actually even pass through the blood-brain barrier. So it's pretty wild. Okay, health effects of ozone, PM, air pollution generally. There are widespread respiratory and cardiovascular system effects. So you might expect things like lung cancer, asthma, pneumonia, but really congestive heart failure, stroke, right? So there's just a wide range of health effects associated with air pollution. So this kind of leads us to why in current day we still study air pollution, right? So I'm kind of shown you that number one, we've done a pretty good job reducing PM and ozone, but we still have some ways to go, right? I showed you this flattening, and I talked about the fact that there are a number of people that still live in areas with elevated levels of air pollution, and the health effects are serious. So how do these pollutants, where do they come from? And another way of asking that is what kind of human activities can be traced to the air? So driving is definitely one of the first things you think about, and that's why this COVID-19 story is interesting. Household cleaning, yes, absolutely. Smoking, yes. And I don't know what this says about me, but one of the things that I found so fascinating when I started grad school was that they measured nicotine and cocaine in the air. And I just thought that was like just amazing, right? Like out in LA, of all these people and all these activities, and you can measure nicotine and cocaine. Deodorant use, yes. Gambling, I don't know. I'm going to say no. Smoking, yes, associated with gambling. I don't think you can measure gambling. Surfing, yes. So we recently, I'm not going to talk about this, but we recently measured surf wax compounds off the coast of California. So you can ask Carol about that. Yeah, so all of these activities, right, we can measure in the urban air. Okay, so that gets us to these sources of air pollutants and their precursors, right? So broadly speaking, we kind of categorize things as being anthropogenic, which means they're human-caused, or biogenic. So, when you smell flowers and you smell trees, those are hydrocarbons, right? Those are the same, they are not, I shouldn't say they're the same, but they are volatile organic compounds that come off of trees and plants. We also call another source is pyrogenic, so anthropogenic, biogenic, pyrogenic. Those are hydrocarbons coming and volatile organic compounds coming from fires. And then all of these lovely smelling things that you use on your body and in your house, right? So these are all sources of hydrocarbons and volatile organic compounds that can serve as precursors to pollutants, especially in urban areas. And I always say your nose is a good guide. Yeah, if you smell something, they're smelling hydrocarbons or volatile organic compounds. Okay, but the number one choice here was cars, right? So that kind of gets us back to COVID-19. So on March 4th, the state of emergency in Los Angeles was declared in California. 19th of March, shelter-in-place orders were issued. And then around early April, around the 5th, you started seeing all of these headlines in the newspaper, right? So the pandemic has led to a huge global drop in air pollution, right? And you just saw coverage of after coverage of these kinds of things. And then the Twitter sphere goes crazy, right? They're wondering if no traffic plays a part in cleaner air. Duh, man, that's a real head scratcher, right? And so, and my friends, they're like, oh, wow, this is wild, right? Is all the pollution just gone? And, you know, part of your brain is going, yeah. But the other part of your brain has been going like, but wait a second. I've been showing this figure for a while about how cars are getting really clean, right? So another part of my brain went, I don't know, right? I actually don't know. So on April 14th, basically a bunch of scientists started getting together online and having these discussions. I wrote a proposal to the NSF saying, we have to go out and measure things right now. We can do it in a way that's safe to our grad students. We can send one at a time. And, you know, we had to think about keeping the grad students safe because of COVID. But it really was this like really cool science moment where, you know, the data are telling you it might not actually be that clean out there, but part of your brain just doesn't believe it, right? Part of your brain just says, how can this even be? So one of the things that we looked at first was meteorology. So I study emissions and I study the chemistry of those emissions, right? So I'm hyper-focused a lot of times on those parts, the emissions and the chemistry, but meteorology is important, right? So pollutants can just be blown offshore or they can be rained out. So this was analysis that one of our colleagues did. And there is a lot going on in this figure, but I just want to draw your attention. I'll just walk you right through it. So the black line is 2020. It's ozone. It's 8-hour average. That's an 8-hour because it's relative to the standard. And down here, 24-hour PM 2.5. Okay, so that's the value in 2020. The months are across the bottom. And then we have a range of values from 2015 to 2019. So you're sort of looking at how is 2020 anomalous, right, to this range of years? Because we do expect year-to-year variability, right? There's a lot of reasons for year-to-year variability. So you kind of look at these ranges to sort of see when we're outside of that variability. So what we see here, and then I should say in the back, we see temperature. So gray indicates like average temperature. Red indicates that we're above average, and blue indicates that we're below average, okay? So what we see is that on the top, when ozone is high, above the average, it appears that we do in fact get anomalously high, if you will, outside the average, or even outside the range of prior years, we get high ozone during 2020. And that high ozone was actually associated with high temperatures, okay? Then on the bottom, these clean skies that we saw, so again, remembering that the pandemic and the restrictions were heaviest in March and April, we do in fact see PM 2.5 being down below the average, right? So it was true, the skies were clear. But this is also a really cool period, and when you look at the rainfall, we had heavy, heavy rain events. So these decreases in 2020 were more likely associated with rain events than having a whole lot to do with the traffic. And in 2020, late PM2.5, you see this very high peak, and that's associated with wildfires. So that just gives you an idea of the magnitude we get with sort of vehicles and then when we get a wildfire. Okay. So now we're going to get a little bit more into the details. So we said, okay, PM2.5 was low, but maybe because of rain. What else is going on? So this just is showing you what was happening with the traffic. So the streets really were empty. I mean, it was amazing. People that lived in LA were super happy because you could get takeout anywhere in the city. You can drive all the way across the city with no problem. I shouldn't say they were really happy. It was a tough time, but that part was great. Traffic was, I keep doing that, sorry. Okay. So what this is showing relative traffic. So if traffic is at 100%, right, pre-pandemic, and then in March, it dropped to about 50%, right? So traffic reduced, and there are lots of ways you can measure traffic, but by most counts, like on-road passenger traffic dropped 50%, okay? So this is, I co-led 2 field campaigns. So one was in 2020, and we took samples in March. We took samples in April, May, and then in June and July. And then we did another field campaign in 2022 to sort of capture these trends during and after the pandemic. Okay, so traffic went down 50%, and then the question I asked you earlier was, what happened with the gasoline combustion markers? Did they go down? Did they go the same? Did they go up? And you would think they would go down, right? But they didn't. Okay, so on to the next. Go back to the presentation. Okay, so now this is I'm showing you now some of my own data out of my group. And this is measurements in 2022. Remember that I've said that CO is a marker of gasoline combustion, especially when you're in an urban area. This acetylene is also a marker of gasoline combustion in an urban area. And I just want to draw your attention to the mean and the median values. So again, there was a 30% increase in traffic over this time period, and we see basically no change in the mean. And again, this goes back to that on one hand, you hypothesize that this is the case, right? That these gasoline combustion markers may not only be associated with cars anymore, but your brain can't get around it. And when I tell you this was one of the hardest papers to get published, none of the reviewers believed it either, right? They're just like, there's no way you didn't see anything. But we didn't. And we didn't see it in 2020. We saw the same thing when we went back in 2022. So basically, we don't see the same decrease. You do notice, perhaps, there's a little bit of an increase in these lowest values, and that's actually just due to the increase in temperature between April, May, and June and July. So you get more evaporative emissions. Like if you think about what pavement smells like when it's hot, right, you're getting more evaporative emissions. So that was what was happening in those lower levels. But what we ended up finding, and again, I will say one of the important things, we have these measurements from 2020, but we also were able to reference measurements that happened in 2020, 2010. So having long-term data records, lots of data are really important for helping us make these findings. But basically, what we ended up concluding is that these gasoline combustion markers, though they used to be dominated by on-road gasoline vehicles, there was now another source. And we concluded that that was probably some kind of off-road mobile source. And we still think probably, especially at that time, it was largely landscaping equipment. So your gasoline-powered mowers, lawn trimmers, et cetera. What I still am looking for is any evidence that, that people, because they were home more, like I don't know if it was at the industrial scale or were people home more and working on their lawns more, right? We don't really know. We don't have the activity data yet to go with it. But one of the things that was interesting to us, which is shown here, is that this is emissions projections 2010 and 2020 by South Coast AQMD, just showing that in 2010, it was expected that the CO from on-road motor vehicles was roughly double that of other mobile sources. But South Coast AQMD actually predicted that by 2020, the CO from on-road motor vehicle would equal other mobile sources. So this is something that those people that are sort of watching the technology and the activity patterns predicted. So I think we weren't wrong about this hypothesis and finding. Okay, but what about other things? So not moving away from this gasoline combustion. So I want to talk a little bit about volatile chemical products. So scientists here in Boulder at NOAA down the street were among the first to discover just how important these emissions were in urban air. And you can just imagine, this is kind of fun to look up, like all the media about it, and it's like Axe body spray and cleaners and all of these things. But so we'll talk a little bit about these volatile chemical products. So these are data now that I'm showing you from our field site from 2020 and 2022. And so what I have shown here is this is a graph of temperature and then isoprene. So isoprene, we think, is like almost 100% from plants. Okay, so this is something that it's biogenic, and it's behaving as we expect, which is that as temperature goes up, the amount of isoprene in the atmosphere also goes up, right? So we have light and dependent emissions of isoprene. It's behaving as we expect. The points are color coded by time of day. Limonene, on the other hand, right, it's that sort of lemony smell, is not necessarily behaving like isoprene in that we do have some temperature dependence and some higher levels in the morning or in the afternoon. But one of the things that we saw that we were really surprised about are these very high levels in the early morning. So these are 5 a.m. samples, and the levels are really high. And we were just like, wow, that's a little bit strange. So we did a bunch of investigation, and we attributed that limonene to being anthropogenic source. So again, this is that volatile chemical products. There was another way that we looked about this. So a lot of people have said, okay, yeah, we see these higher values in the morning, and that's just because something called settling of the boundary layer and less chemistry. So these compounds are emitted, they don't react with anything, and basically as things cool, the mixing volume gets smaller, right? So that just, like, we have a smaller mixing volume, so the concentration goes up. So we ran a model. So what's in this other figure here is that each of these lines represent a model simulation where we only used plant emissions. And so you can see that in the evening, the concentrations start to go up, the mixing ratios go up a little bit because of that lack of chemistry and lower mixing volume. But the values that we were measuring are way, way above in the morning, above what we would expect from just the biogenic emissions alone. So we just submitted this paper a little while ago. We think it's one of the first to definitively demonstrate that these early morning terpenes are probably from anthropogenic sources, and they may have a unique impact on chemistry there. Okay, so moving into the last part of my talk tonight, I just want to talk a little bit about where we are now. So this is a similar figure to one that you've seen before, but it is a different time period, so 1990 to 2022, and it shows all of the criteria pollutants, again, different averaging times, but in this, on the right side, what you'll see is both a legend as well as the changes in each of these pollutants between 1990 and 2020. But one of the things that I want to draw your attention to here, this is percent above or below the standard. So you'll see, and this is what I was talking about before, so this is average over all locations in the US, is that PM2.5 and ozone is just hovering near that standard. And it's really been flat, right? So in a way, cleaner vehicles was the low-hanging fruit, if you will, right? So now we're sort of in the situation where we have PM2.5 and ozone that's at or near the standard. And so there's still a lot of work to be done in figuring out, what are the causes of those? How do we mitigate that? One of the things that I wanted to show you is some PM2.5 trends. This is kind of interesting as well. So again, these are years. Each of the bar represents another year, a different year, so 2000 to 2023. And the numbers are the number of days above the standard. And what we see is that, there has certainly been, especially in places like LA, a reduction in the number of very unhealthy days, right? So that's good, but the number of days above the standard is still fairly high. You can look at this for other cities as well. So we have this Dallas-Fort Worth area, and again, some years higher than other. We don't have this consistent downward trend anymore. Except for some reason in New York, and I don't know what's happening there, but something looks like it's going well. There, good reductions there, so I'm not sure. I have to figure that one out. And then this is Denver, right? So again, we have fewer days than LA, which is not surprising, but still, like in 2021, almost 70 days above the standard. So again, this is just a little bit of a where we are now. Okay. So I wanted to, this is my last slide before I just wrap up. Recently, I published an editorial in Science Magazine with a co-author, Kim Prather. And one of the things that we are asked a lot in this field when we're going out and we're doing measurements is whether the air is safe, right? Some context could be after the fires here, after the fires in LA, right? People want to know, is the air we breathe safe? And that is a really difficult question to answer. One of the things that we said in this piece was that we have to modernize our air quality standards, right? So I've dropped these hints throughout, but to say that that list of chemicals, compounds, right, hasn't changed since 1970. We are able to measure more things in the atmosphere, and we are finding more things in the atmosphere. But there's a challenge just once you measure something in the atmosphere, we still don't necessarily know what the safe levels are, right? So if you think about that AQI metric, you have to relate the ambient concentration to some kind of exposure limit. So we're lacking those. So one of the things we've thought about, and this to me is just kind of a call for action, I like to think about what can we do, right? So we have the advanced instrumentation, and it's getting better all the time. There's often new instruments being developed. And so thinking about establishing collaborative networks. So oftentimes there's just one or two of us out doing our thing, making our measurements, but thinking about how we can coordinate in these measurement networks, how we share data, how we standardize data, right? So there's a lot of opportunities to create a more coordinated system and move the whole air quality assessment into the 21st century. So I said some of this already, right? We can measure a large number of pollutants and precursors. We would benefit from more coordination, and we need to figure out these ambient exposure levels. So, one of the things that we can think about doing is, right, if you have maps of where measurements are being made and what kind of sources are nearby, and then, someone can be collecting health data as well, right, to help us link all these things together. And this is a perfect sort of, everybody wants to do AI, so this is like a perfect AI opportunity here. And I haven't been reading all of my little blurbs at the bottom, but this is an important one, is that funding and partnerships really remain critical to moving things forward. Okay, so take-home points, here we are. These science, engineering, regulatory partnerships were very successful in reducing emissions from gasoline vehicles, right? And lowering ozone and PM levels in LA and other urban areas. It's not just the cars. Ozone and PM levels remain near or above national standards, and really many sources at this point are contributing to that ozone and PM. Things, we talked about volatile chemical products, we talked about off-road mobile sources, we didn't talk about cooking emissions, but that's another one. This AQI is a super convenient metric for communicating risk and sort of knowing where you're at. Should you go for a run? Should you not go for a run? But just to keep in mind, it's based on PM 2.5 and ozone, so we probably need to add some new compounds, establish new exposure levels and standards. So we do have some work to do still. And I do love my job. I'm a little nervous, but I love science, and hopefully you found that out a little bit today. Okay, so acknowledgements. So collaborators and contributors to this work, the UC Irvine folks, we were making measurements, University of Colorado. I wrote the piece with Kim Prather. Yost was on those calls that we had early pandemic days trying to figure out what's going on. My research group really is, they keep me going. Most of these people have graduated and left my group, but this is that, you can see I'm wearing a mask around my neck. So this was that, one of the first gatherings we had. This was right around the time we were doing that study in LA. This is my awesome group of graduate students and postdocs at the time. And here at NCAR, Peter Nell, just an inspiring lab director, and the Explorer Series team that kept me on track for the most part, and here we are. So thanks so much.
Excellent. Thank you so much, Kelley, for that wonderful talk, and just really highlights this interesting story that kind of goes against what you think or maybe just suppose what's happening in the environment. So folks, we're going to do our Q&A session, and we're going to kind of rotate between online questions and in-person questions, but I'll take any in-person questions first. Does anyone have a question for Kelley in our audience? Yes.
As near as I can tell, in the Denver area, our ozone performance has been abysmal for years and years. Would you care to comment on our success or proposed measures or anything that would let us know whether that's likely to get better?
Yeah, so I have not, I'm going to parse this in two ways. Number one, there was a Front Range talk, Explorer Series talk, that's available online. I personally have not been doing work in the Front Range in recent years. My understanding is that the sources, the most likely sources of ozone in the Front Range are not being regulated that well right now. And so will it get better? Probably not without that. So probably not, without this story that happened in California, right, which is identifying what the sources are, being willing to pursue the engineering and the regulations to change that. And I think that's the best answer I can give, yeah.
For my online folks, if you have questions, you can scroll down again, and it just has a Q&A tab right below the Slido platform. But we'll go for another in-person question here.
You said that ozone and PM 2.5 are your big worries of the criteria pollutants. What toxic pollutants are top of the list? And what are the sources?
That's a great question. I think it's highly variable. So again, my recent experience has been in the LA area. So in the LA area, they are doing a better job of doing sort of routine monitoring of air toxics, and we are starting to get a handle on, what toxics are elevated and what are associated with certain activities. I wish I could give you a specific list. I can tell you that, I've been doing some recent work at the California-Mexico border, the US-Mexico border in California, and we are measuring a lot of compounds in the air that are associated with raw sewage. So sewage is being, right, exactly, that face, it's awful. So hydrogen sulfide and some associated pollutants. You know, the fires are an obvious concern, right? When these fires move into what we call the WUI, the wildland-urban interface, and you start burning batteries and plastics and vehicles, right? We have a lot of metals and air toxics. So unfortunately, I do think there are a lot of sources. I think that the question, though, where I would like to see us get a little stronger is that, you know, it could be, they're not always too high, right? So I just want to be really careful, right? And saying is that, and first of all, and we don't always know what the safe limits are either. So I'm kind of not giving you an exact answer there, but that's just to say that we do measure all kinds of things in the air, lots of air toxics at lots of different places, but we're still trying to assess like the concentrations and yeah.
Excellent. I think we're going to have one online question that we're going to pull up. No. What do we do to clean air that is unhealthy for us? Is it only time?
What do we do to clean air unhealthy for us? If I think I'm going to interpret that question as, is it unhealthy being there for? Is time the major thing? So exposure time is important, right? I think if that's the question. So being in, but it is also the level, right? So very high levels for short duration are unhealthy for us. Moderate levels over long periods of time, right? So increasing your breathing, you know, doing things like running when PM and ozone are high is not a good idea. So it's time and it's concentration when we're thinking about unhealthy air and exposure. And I hope I interpreted that question correctly.
Thanks for that. I know we had a in-person question in the back here.
Okay, this is a little bit more simplistic, but I'm just trying to wrap my head around. So you said that, you know, with car emissions, we've seen that got a lot cleaner. And some of the other sources we've been able to identify is cooking, and like, what did you say, like other motor vehicle or other motors like lawnmowers or whatever. Do we know what specifically it is about cooking? Is it like turning on your oven or like using this spray for your pan? Like, I'm just trying to wrap my head around like what exactly creates like those emissions, and then also, is there anything that we can do just as people who are trying to improve these conditions to be more conscious of those emissions?
Yeah, so that is a great question. There has been a lot of, so there's sort of two levels that cooking emissions are important, right? So I want to talk about sort of a neighborhood scale. So there's been some really interesting studies where people have like driven a mobile van around that measures pollutants. And when you get to the restaurant row, right, there's just really high pollutant levels. So, you know, it's kind of interesting. We think, oh, we want to live in concentrated urban areas where we're not driving, and then there's a block of restaurants, right? So it's always a challenge. But so that's sort of the ambient level, and that's a lot of you know, it's probably a lot of grease cooking and exhaust just going right into the ambient atmosphere. So there's not a lot of, again, regulations on what's being emitted from like restaurants, and that's large-scale cooking. There's been a large number of very interesting studies that I have not participated in on indoor air, though, and looking at exactly what comes off, what compounds, what pollutants come off of like every single activity. So you ask about spraying your pan, turning on your oven, cooking this kind of meat or that kind of meat or these kind of vegetables or using this kind of oil or using your toaster. So there's actually almost like exhaustive information now about what happens in a kitchen. And so, that doesn't necessarily, I guess there's a question, but that's for indoor health, home health. And, things that you can do there are really to have really good exhaust fans, making sure that you are using good exhaust fans. No one wants to hear it, but gas stoves aren't the best. They're lovely for cooking, but these are some of the things that add to increased emissions. Yeah.
Awesome. Thanks for that question. I think we have another online question. How much do Western wildfires contribute to atmospheric pollution?
A lot. So when we talk about where we are relative to the standard, we get what's called exceptional events for wildfires. So when I show you PM 2.5 and ozone levels over time relative to the standard, wildfires are taken out. Okay, so that doesn't include wildfires. But if you'll remember, I did show you that PM 2.5, I had this one figure just to give you an idea of the magnitude. Where were we? Right here. That this is just an idea of the magnitude, right? So this is, like half a month of September, and sort of the average 24-hour PM 2.5 is around 10, right? And then you have, weeks here getting up to 40. So PM 2.5 and ozone and CO, these are all ozone is trickier, I will say. I should be careful about ozone. Ozone can be formed and also can be titrated from smoke. But PM 2.5 concentrations increase drastically because of fires. And then again, as I mentioned, if you get into sort of this wildland-urban interface and you're burning non-vegetative fuels, you can end up with a lot of air toxics. So mitigation of air pollution from wildfires is a real challenge in the West, I think. And it's a big part of our research portfolio at NCAR is kind of thinking about the air quality effects of fires and what can be done.
Looks like we have another online question here. Do you have any data about the number of days per year above air pollution standards after wildfire-caused days are removed? While bad air is bad, if fires are overwhelming the data, we can't tell what, if any, progress is being made.
I've wondered about this, and I have looked, but it's been a while. So I was trying to find this information once. So I think, the question is, how many exceptional events are there, right? And if you actually added back in the days from wildfire smoke where we would sit. So I've looked for this information. I don't remember the numbers offhand. Scientific publications that have just getting a little bit away from where we are in relative to the standards, right? So not in attainment or non-attainment, have definitely shown that there was a really nice paper that came out a few years ago talking about ozone and PM from wildfires and just sort of saying, we've sort of wiped out the gains that we've made, right? So on balance, the improvements that we've made in vehicles, for example, if you do start to add in those fire events, we don't look as good as we did.
Do we have questions from the in-person audience? Questions there? I actually had a question on one of the VOCs you were mentioning. I think it was limonene, I think. And you were saying that the current thinking is that it's anthropogenic. And are there certain sources, I might have missed it, that would lead to those big spikes you're seeing in the morning?
So I am trying to figure this out. They're very common in cleaning products. So one thing that I have not been able to figure out, so one thing about the measurements that we made is we didn't make high time resolution measurements. So we see them in 5 a.m. samples, but like we don't have measurements throughout the night. So for example, I am not sure if is there a lot of cleaning that happens, like industrial facility, like commercial cleaning is happening at night or early morning, or if is it more like in a manufacturing sense? And someone else might know more than I, but I've been trying to think about this, like what's the actual source? But they're certainly cleaning products, and having a little bit higher time resolution data, I think, will help us figure that out. Like, what time do they actually start getting high? And yeah.
Thanks. Oh, we have a question from.
Just to follow up on his question, is it considered a precursor to ozone? Is that the concern?
Yeah, ozone and PM 2.5. It's quite reactive.
Excellent. Do we have any more online questions? Yeah, we're going to go ahead and. Could short-term enhancement in air quality observed during the COVID-19 pandemic have an impact on the perspectives of long-term environmental researchers?
We certainly, again, I'll try to answer this question. If I'm just going to interpret it one way and say that we did learn, right? We did learn there some things went down, nitrogen oxides went down, right? So in terms of the short-term enhancements, changes in PM 2.5 were uneven, right? There's some really interesting studies in LA showing where PM 2.5 sort of spatially went down and where it went up, right? So we certainly did learn something. It was not that there was no reductions. So I think that it is fair to say that when you take even a closer look and a different look than I've taken, you sort of, there were really disparate impacts of COVID-19 on air pollution, right? So some neighborhoods didn't see these big reductions. If you were in an area with heavy truck traffic, for example, you didn't see it, whether if you were in another sort of more residential area, you saw it. So I hope so. I hope that we, take what we've learned and put it into the long-term perspective for sure. Yeah.
Awesome. Do we have any more in-person questions? Yeah.
Thanks, Kelley. That was really interesting. Actually, my question is about the PM 2.5 reduction in this plot, in this figure here. You said that like the reduction between March and April, which was like the lockdown was the strongest, was due to rain events, like more rain. I was wondering if you have like, it's probably on the paper, but do you have a reference for like how much more rain observed during this period? Because like March and April is like spring, so we expect to have a lot of rain in the other years as well. So do you have a relative difference between those previous years and the COVID-19 year about the precipitation?
Yeah, so that is a good question, and I don't have those numbers, but what I will say is that in March and April in Pasadena are not necessarily that rainy. So you're right, like here and other places we would expect a lot of rain events, but the winter rains are usually, they sometimes go into March, but again, yeah, we're anomalously high rains.
Excellent. I think we had another question down here. Yeah.
You read a lot about microplastics and its effect on human health. I didn't hear you talk about that. Is that folded into PM 2.5, or is the atmosphere just not a vector for it?
I would love to tell you that the atmosphere is not a vector for it, but that's not true. There's been a lot of recent work about microplastics and their transport in air. It's not something I've studied, but I recently, for example, I spent some time in New Zealand, and there was a woman there that I learned a lot about microplastics in the environment. So we absolutely, I think a lot of our PM 2.5 measurements are filter-based, so it's just a weight-based measurement, but we're getting a little instruments now that are looking more at the composition of PM 2.5. We're starting to see studies of how much of that PM 2.5 or even some of the smaller particles are actually microplastics. So, yep, it's there. And yeah, I was a little bit surprised, actually. I don't know why, but I didn't want to believe it. Yeah. So there we go. We can't end on that note.
No, I think we won't end on that. Aaliyah, do we have another online question? We're going to go ahead and project that. There's a push in Colorado to reduce organic matter from landfills to reduce landfill methane emissions. Do you think this is a worthwhile effort?
I am not familiar with these specific efforts. I can just say in the state of California that this has been methane from landfills is a significant source of greenhouse gases. So I didn't talk too much about greenhouse gases today. I talked largely about the pollutants and precursors of criteria pollutants. Methane is a greenhouse gas. It's a little bit in a different criteria or different category, and not something I have studied. So I have to punt a little bit, but just to say that, certainly this research is going on and these efforts are going on in California, and they've decided it was worth it. So maybe we look to another state, but yeah, methane is a potent greenhouse gas. And so that's what I can say. Yeah.
And we got a question here from an audience member.
Do we know kind of to what extent different VOCs have different effects? Like are all VOCs more or less equal in terms of their effect on pollution and human health? Or like I think of smelling a flower or a pine tree or something like that as being good and beneficial to us, but are those sort of equal to any other VOC?
Yeah, I love this question. This is a great place to end. This is a great question because I think it's like such a complicated answer, but also gets into what I love about VOCs is just the diversity is insane, right? So when we think about their chemical reactivity, they behave very differently. So some are really efficient ozone producers and some are very efficient PM producers. And from that perspective, if you make a lot of ozone or you make a lot of PM, it's not great, right? And even some of the things that we really like the way they smell. Also, this is a little bit unrelated to my talk specifically, but a lot of these fragrances are used in like vape pens and things like that, right? So again, if we heat these things, they kind of then have this whole other range of toxicity and properties. So they're so varied, right? They're so varied in their, so a lot of it is really their chemistry and what happens when you heat them or put them in the ambient atmosphere, right? And so their native properties may not be the same. Probably like pure toxicity, it takes a lot of any of those things to actually be toxic on their own, which is why they are used as flavorants and for fragrances and things like that. Yeah, so walking through the forest is still highly encouraged. Yeah.
Awesome. I'm just going to cap it off with my last question for you. It's clear just from my conversations with you and from your presentation that you love your job and you love the work that you do. So would you have any advice for folks, either graduate students, undergrads, or even high schoolers thinking about getting into this field? And the trends that you're seeing.
Yes. The piece of advice that I always give is never to opt out. And that is to just go with the flow a little bit, right? So there's a lot of things about science that are daunting. And I can just remember at every step of the way, can I get a degree in science? Can I get a degree in, but then you're just like, well, I like this, so I'm gonna keep doing it, Did I ever think about getting a PhD? No, I didn't, but I really loved what I was doing. And so I kept going in school. Did I think about being a postdoc? Not till sort of the very end. So kind of at every step of the way, I just really loved what I was doing. So rather than say, and I talk to a lot of young women, especially, right? Like, oh, can I be a mom and be a scientist? And you just again, you just try it, and if it's not working, then make another choice, but don't opt out before you have a chance to test something out. So that's really my general advice, is just to try it, and then if it's not working, make another choice. But until you get there, it's not worth, opting out, because you're afraid of, it's easy to be afraid of, can you make it? Can you find enough money? Are you going to be good enough? But until someone tells you you can't or you're not, then you just keep going. Yeah.
Well, thank you so much, Kelley. Why don't we give her a round of applause? Kelley will be around for a little bit afterwards to answer any more questions. I have a couple of housekeeping things before you leave. I just want to really thank you all for coming again in person. It means a lot to our team and for the thoughtful questions that you had. If we hope to see you all again online or in person on June 6th at 7 p.m. for our next event, where we will chat with Courtney Payne and Ann Linderman about the intersection of art and science on Arctic marine ecosystems, and featuring a short animation about how environmental change are affecting phytoplankton. If you're interested in more NCAR Explorer Series events, check out our website for upcoming lectures and conversations, and to view recordings of past events, especially if you're interested about air quality in the Front Range. We have a great lecture on our website about that. If you are 18 years or older, which looks like some of you are, please take a moment to fill out our 3 to 5 minute anonymous survey to help us better understand the impact of the program and how we can improve for our next event. That survey is going to close on Monday, this upcoming Monday. You can find the survey by scanning the QR code, which will pop up right soon or here. And with that, I hope to see you all next time on June 6th or in the future. Thank you again for attending.